Hello everyone. Now, today's lesson will be about PID controller design and phase lead controller design. Now, we've talked about PI controller and PD controller design previously, but we didn't actually look for the best controller in terms of dominance or the controller that is the closest to the requirements. We didn't really look at that problem. We just introduced you to the controller, to the concept that there could be a derivative effect. So we could use the error and its derivative included into the control signal, or we might also use the integral of the error, which actually helps us out in order to track the step type references. Now here we will generalize the PI and PD controller, which is basically the PID controller. If you take d equals 0, you will end up in the PI controller, I equals 0 will give you a PD controller, etc. Or using I and d equals 0 gives you a PID controller. So this is the most general form, the PID controller. That's also the reason why we call this a PID controller. Now we will look at the PID controller design from different perspectives, one of them being the pole zero cancellation, tabulation, and Ziegler-Nichols methods in order to tune the PID parameters. Then we will repeat this for the phase lead controller. Now, let's first start with the pole zero cancellation and how we can solve that. Now, if we look at the requirements, we have 10% overshoot requirement and a settling time of 4 seconds. So let's maybe begin with that. So the settling time should be equal to 4. The overshoot should be 10%. So I've written down the requirements. So having the settling time and overshoot given, or maybe peak time, rise time, or any two of these transient behavior definitions, then it is possible to conclude and work our way out to come up with a pole pair that should be dominant. So having only one would not be sufficient. There would be one unknown parameter, but in this case, we know what the poles should be. So let's start with that. Now, in a case where we have the overshoot and settling time values, we should basically start with the zeta value here. We should determine what the zeta value is, because it only depends on the logarithm of overshoot divided by the square root of pi squared plus log overshoot squared. So this should give us the zeta value. And since we know what the settling time formula is, namely zeta times omega n, we can use this formula in order to work out what omega n should be. So we know what zeta is, we know what settling time is, so this should give us the omega n value here. So let's look for the zeta and omega n values that we need to accomplish here. Now, we did forget the multiplication sign here. So there we go. Now we can see that the zeta value is equal to 0.5912, and then we have the omega n 1.6960. Now, if you want to know what the exact point or location of the poles are, we might go ahead and do the following. We might use the square root 1 minus zeta squared times omega n. This will give us the real and imaginary values of the exact point that should be used. So we can see that the real part should be equal to 1 and the imaginary part should be 1.3644. Now, let's try to come up with a PID controller design using pole zero cancellation. Now, if you remember in the previous example, in the previous lesson, we did have some pole zero cancellation. Now here, what we can do is we can go ahead and choose one of the poles and choose the zeros exactly on top of that pole, so that the PID controller design becomes kind of a PI controller or PD controller design. So what I mean by that is the following. Since we have the zeta and omega n values, let's go ahead and define our PID controller. Now, as usual, I'm again being a bad example here by choosing Z1 and Z2, the zeros of the PID controller, because if we are going to use the algebraic method, what we should do is we should define Kp, Ki, and Kd as real values, as symbolic real values. And if you're using a pen and paper, and if you're in a classical exam, you should do the same. But for the sake of our discussion of today, I'm going to use Z1 and Z2 again. I didn't write real because that would narrow down the available controller parameters, because I would have then decided that all the zeros should be on the real axis, which is not a necessity. So therefore, I'm not using the real value, but I know that the K gain value here, or the p-type controller part of this controller, should be a real value. So our controller would look like this. So K times S plus Z1 times S plus Z2 divided by S. So this would be our controller. And by the way, I didn't write down what the system looks like, so let's also define our system. So TS equals 100 divided by, or TF, so 100, we don't have any 0, but we have the following polynomial. Now, it is possible to use s squared plus 7s plus 10, and then times s, namely s cubed plus 7s squared plus 10s. But you can also, again, use MATLAB to solve this. So we might use convolution here. Convolutional vectors corresponds to multiplication of polynomials in our case. So we have one at 2, one pole is at 2, one is at 5. So these are basically s plus 2 and s plus 5. So the multiplication s plus 2 and s plus 5. So we need another convolution here, or another multiplication. And we'll choose 1 and 0 here. So this will give me the coefficients that will result in multiplying s plus 2, and s plus 5. And you can see it is the case. So you can define your transfer function based on the convolution of vectors. So this helps me out in determining what the poles are, or it is given by definition in terms of poles. So I like to use this here. So let's define also the symbolic version in order to be able to use it. So 100 divided by s times s plus 2 times s plus 5. There we go. Now, this is our controller. Now, if I'm going to design a controller, the next step would be to calculate the following closed-loop transfer function. Fs times GSS divided by 1 plus Fs times GSS. Now, this multiplication is pretty important because this is actually the term. Let me also take this one here. That will be calculated. So this multiplication is important because this exact multiplication, if I leave out the k here, the gain of the p-type part, then if I'm going to design such a controller using the root locus method, this transfer function would be used to determine the root locus. So our locus and then this transfer function. So therefore, we have a divide by s. Here's another one. So two poles at the origin, and then we have s plus 2 and s plus 5, which means that at minus 2 and minus 5, we should have basically poles. And then the two zeros of the controllers should also be on the root locus, so we should place one zero at minus z1 and the other one at minus z2. And at this exact point, an idea would be to use a cancellation, because that would narrow down, or that would reduce the system into a lower order system. And therefore, it would be much easier to try to come up with a controller. But choosing one of the parameters would be very restrictive, and we'll see if that's really the case. since I would fix one of the parameters that was freely changeable before that. So let's, for example, assume that we use s plus 2. So that means that let's get rid of the pole at minus 2 by choosing a 0 at minus 2. So if I do such a thing, then I would say that Z1 val, let's say that's the one that we get rid of, is equal to 2. So this is by choice. Now if I do such a thing, then I would also immediately have to change Z2 into real, because the poles are real and I'm getting rid of one of the poles, and it is not possible to have this one real and this one complex. So therefore this one should also be real, because the coefficients of this multiplication should be real. So therefore, if I do such a thing, this would be then the controller here. And I should then maybe simplify TSS, and let's call pretty TSS. Misspell. So now we can see that this is the end result. Now, if I would have used Z1 and Z2 here, I would end up in a fourth order closed loop transfer function. The reason is that the system is already a third order one, and my controller adds another pole, so it should be a fourth order one. But due to the pole zero cancellation, we got rid of one of the poles and one of the zeros. So this is kind of a reduced version of the closed loop that can be achieved here. And I have only one zero and a third order closed loop. Now it is obvious that by choosing basically one of the zeros and adding it to this multiplication here, I can also see that I'm basically determining or trying to design a PI controller here. And the reason behind that is that instead of having this controller and the system that we have here, I have decided on the position or the location of the zero, so my system is updated. My system is a third order system with a zero, and I'm trying to come up with a PI controller. So using pole zero cancellation basically gives me the ability to reduce the problem into a PI controller design, because I've decided on the zero here. So therefore, it is possible to use this. And another choice would be to choose 5, or I might also go ahead and try to cancel this S term here. But of course, choosing S here is not a good idea. The pole zero cancellation would happen at the origin, and the origin is one of the marginal stable points that you don't want to mess with. So if we are trying to cancel pole and zeros, we should be looking for stable pole zero cancellations. Therefore, they should be on the left half plane, not on the marginal stability axis, j omega, or even at the origin. So if this is on the right half plane, I should never, ever, ever go ahead and cancel this here, because if this is applied in a real system, then this would be very dangerous, due to the fact that the cancellation might not happen exactly at the point that I expect it to be, because of, for example, parametric variations. If we, for example, have a certain thing that heats up, and with this heat, if the mathematical model deviates from the nominal transfer function, for example, model, then this cancellation would be inexact, and at that point I would have an unstable closed loop. So therefore it's risky and permitted to cancel poles and zeros in the right half plane, or even on the j omega axis. So this should happen on the left half plane. So therefore, I can only get rid of s plus 2 or s plus 5. Or another idea would be the following. I could also go ahead and choose a z2 here. Namely, one could be equal to 5 and the other one could be equal to 2. So that would end up in the following. I would choose this here, and let's see how it affects our system. Or let's use pretty. And there we go. Now, if I cancel both zeros, or both poles with the zeros of the transfer function of the controller, or directly the controller, then I end up with s here, and the controller has also an s term here. So therefore, it corresponds to 1 divided by s squared. And I'm kind of designing a p-type controller for 1 divided by s squared. So this is the end result. So no matter what k is, I will be on the j omega axis, and this design doesn't make sense, of course. But if this, for example, was somewhere else, let's try that out. Let's say we have s plus 3 here. Then this might be a valid choice. As you can see here. In this case, I might go ahead and choose this whatever I want. I'm ending up in a stable closed loop. But you can see that a third order system, a first order controller, should end up in a fourth order closed loop, but we have a second order because we have two cancellations. We basically reduce the problem here. Now, but pole zero cancellation is not always the best because of parametric variations, noise, measurement noise, the incorrect modeling of the actual system. So therefore, we should be carefully acting here. But it is a design choice, and theoretically, we can go ahead and cancel the zeros and poles. So let's return back to our discussion here. Let's change it to S. So canceling both at the same time is not a good idea. So let's get rid of this. Let's have still a parametric Z2 here, but we know that it is real. So in this case, we can see that we have a third order polynomial. So since we know what zeta and omega n is, we can directly construct our design problem here. So let's have num then, and let's say coefs of then, s, and then all. And let's also normalize our coefficients here. The highest order term should be coefficient 1. So now we have the PCS, the characteristic polynomial, on one side, and we can also construct the s squared plus 2 times zeta times omega n times s plus omega n squared part, because we know what zeta and omega n are, but we need another pole. So let's have PES, s plus p, because it's the third order. So let's have the polynomial here, coefs of PDS times PES, s, and all coefficients. And the problem would be to have PCS equals pole, and then we would look for a solution. But before that, let's cycle through each equation in this problem and display the ith equation numerically. So let's see. Now we can see that the first equation is 1 equals 1, which I have tried to accomplish by dividing the whole polynomial into its highest order term. And then we have 5 equals p plus 2, 100k is equal to 2p plus 2.862, and then the last equation here. So what are the unknowns? Well, p, k, and z2. And that's basically it. And then we have also 3 equations. So 3 unknowns, 3 equations means that I have a unique solution. And also, I can see that P is positive from this equation, which is a good thing here, because this means that if P is positive, I will have a stable closed loop. Therefore, having a positive P value is a necessity here. If this would have been a negative value, if P would have been negative, then I would not design a controller, because this controller would end up in unstable closed loop transfer function. So yeah, let's get the solution here. And let's assign some variables. Sol.k should give me that. And then we need the z-val or z2 val. Should be z2, and let's have also p-val. We don't really have to extract the p-val information here, but we could, so let's do it. So let's see, k-val, z2 val, and p-val. There we go. Now p-val is positive, we can use k and z here. Now remember that we fixed the z1 val equals 2, so if I'm going to define the actual PID controller, so verification step. So if I'm going to define the PID controller, what I can do is I can use k-val here. That would be the gain. And then I need the multiplication of the following, one z2 val and one z1 val. And of course I have a pole at the origin, so 1 and 0. So let's run this. By the way, I need to get rid of the 1s there. So there we go. Now our PID parameters are the following. This is KD, so KD is equal to this. KP is this one, and KI is this one. If you're not sure, you can just directly divide into S. You can see that this would be S times this plus this term on its own, and then plus 0.1717 divided by S. So this would be the integral part, this would be the proportional part, and this would be the derivative part here. So, of course, if we use ZPK here, we can also determine the poles and zeros. So one of the zeros is chosen to be at -2. The other one is at -96, minus 0.9687. And then we have this gain value here. So at this point, we need the verification. So we need to verify if the closed loop does satisfy the requirements. So therefore, let's calculate the closed loop transfer function. Now at this point, let me open up a figure, use subplot, side by side, hold on, grid on. Now here I want to plot the step response. So let's get the step response of TS. I might also go ahead and get the step info. So the info about the step response. I'm going to get the transients here. Now let's plot t comma y with, let's say, black and then a thicker line. And maybe we might also use the display name here in order to display some data. So let's have ts and then string info.settling time. And then overshoot plus, again, string info.overshoot. So I'm kind of displaying the settling time and overshoot values in the plot itself. So if you do that, you should also go ahead and say legend and then say show. This will be displayed in the legend, therefore. Now let's also have subplot 2 here, where we are interested in the root locus in order to see what's really happening. So our locus, there we go, of something. Now this part is crucial because we have to think about this a little bit. Now, if you want to plot the root locus for a certain controller design problem, then you should always remember that we need the dynamics of the controller and the system, and we need to multiply them. So all the poles and zeros of the controller are added to the system in feed forward. So therefore, we need to use the following transfer function. Now this will look like the controller itself, but I'm not getting the gain part. The only difference is that I'm leaving out kval. If I'm not doing this, I need to look for gain 1 on the root locus, but that doesn't make much sense for me. So I'm going to leave out the kval here, and I'm going to define something like this. So let's say this, and then times gs. Now we can go ahead and plot the root locus of this. What we also can do is we can determine what the poles and zeros are in the closed loop PC map of TS, and we can also plot all the poles here, C poles and imaginary of C poles, and place X marks, so line width 2, and we can repeat this for the zeros with circles. So there we go. Now, last but not least, we might also display an S-grid here, and we have the zeta value and omega n value. We know what they are. So let's run this. And we forgot to change this. There we go. Now let's zoom in. Now, the settling time requirement was to choose 4, but we end up in 4.61. And the overshoot value was to have 10% overshoot, but we can see that that's not satisfied in this case. We have a much higher overshoot, which is also obvious from the step response. And if we look at the root locus plot on the right, we can see that there is the zeta value. Okay, there's no problem. And we have an omega n value, 1.69. Again, no problem. But then we have a 0 at this point, at approximately 1, which is not good. And if you remember the previous lectures of the laboratory, we've talked about the dominance of the poles, and if they are dominant, then the formulas are valid, etc., etc. But in that discussion, we've also talked about the fact that adding a 0 in the dominant region is much worse than adding a pole in the dominant region. And it did affect the overshoot value. And as you can see, again, we have not that much of a overshoot value that we were looking for. Now, one of the poles is here, which is also not that dominant. We have 1 here. The real value of this was 1. Now we have exactly 3, so it's 3 times the value of the dominant pole pair. So yeah, it's not even close to our requirements, and we have also a 0 in the dominant region. So this is not a good design in terms of a PID controller design that should be assigning the poles dominantly. So a dominant pole assignment problem here has not achieved much. So I cannot directly conclude that this is the limitation of the controller because I fixed one of the zeros at this exact point here. That was my choice. So I cannot blame the controller itself if I'm choosing the fixed part here and if it's not a good choice. So one idea would be to maybe repeat this for z2 equals 5 or z1 equals 5, exactly. So yeah, let's repeat this. What we can do is we can go ahead and use a little for loop here. So z1 vec. And here in this vector, I might choose 2 and 5. And then I would repeat this whole thing here for the following. For I, did we use I here? We did use it. So for j equals 1 up to length 2, or we could also directly code it, so maybe 2. So, but I'm going to stick to the length here. So then I'll choose z1 vec and the jth element of this. Of course, I've used j. I could use z1 val equals z1 vec here, a for each loop, but I'm not going to do that because I'm going to use j here in order to separate them like that. So let's run it again. There we go. Now we have both possibilities here. Let's place them side by side and see what's really going on here. Now, interestingly, we have a much different result than the previous one, but there's something concerning going on here, as far as I can see here, and that is the following. We have a pole zero cancellation at this exact point here, at the origin, which we were trying to avoid. Now, theoretically, I can see that it seems to be working because we have cancelled basically the pole at the origin and also the pole at -5. Since there's no other zero, no other pole, we have a second order system. So maximum dominance or infinitely dominant. So, and choosing the zeta and omega n values would give us the result here. But the controller itself might be a little bit interesting. So let me see if it's still defined here. And of course it is. Because of the pole zero cancellation here, I can see that this S and this S cancels each other out, and we are not designing a PID controller, but we have a PD type controller. Now, is this usable, or does this have any meaning? Of course it is usable. Avoiding the pole zero cancellation at the origin is mostly because of the fact that the system has a pole at the origin, and I'm adding a controller 0 at the origin. And if that's not the case, then I might mess up the whole thing here. But here, the pole zero cancellation does not actually happen in the system. It happens in the controller. So which means that it kind of reduces down to a PD controller because it cancels out its own integrator with one of its zeros. So this is much different than adding a zero, the controller 0, on top of a pole of the system. But still, this means that we can use a PD type controller. So if I redesign my controller, but get rid of the integrator and one of the zeros, so if I start by designing a PD controller, I will get a nice working PD controller. Now, this PD controller, by the way, is also a special PD controller because now the system itself has an integrator, as you can see here, and therefore I can track the step type inputs. Now, if we are trying to determine whether I can track a certain type of reference, we should go ahead and look at the system type. If it's a type 0 system, that means that it has 0 poles at the origin. So therefore, it cannot track step type inputs. If it's a type 1 system, then the system has 1 pole at the origin, that means that it will track step type inputs. And if I have s squared, if the system is a type 2 system, then it will track RAM type inputs, etc., etc. Now, it kind of boils down to the following. If the system is a type 1 system, it can track step type inputs even if you use a p-type controller. Therefore, by getting rid of one of the poles, you can easily design a PD-type controller. And you can see that it shows us that we need a PD controller for this, and we should also get rid of this 5 here. Now, the fact that we need to cancel out 5 is based on the settling time value. If you look close, you can see that the real value should be equal to 1. And if you have one pole at the origin, one pole at -2, the intersection would be at -1. So therefore, the settling time would be satisfied on this line here. If we would have updated the settling time in line 6, the definition here, and for example, if we choose a different settling time other than 4, then this would not work. But it's a special case, and it says that a PD-type controller for this system, for this settling time, seems to be working. And the system type is equal to 1, therefore it can track step type inputs, therefore it's a good choice. Now you can also see that the settling time formula has a certain accuracy to it because we've chosen 2 poles and they are exactly on zeta and omega n, but still we have a bit difference in the settling time. That's because of the formula. So therefore, we have to check where the settling time is actually valid with high accuracy. So now this is one way of designing a PID controller, which ended up being a PD-type controller for this system, for this settling time again. You can go ahead and change the settling time value, and you will see that we need to design a PID controller. So we've achieved this design by fixing one of the zeros, and we saw that we cannot fix both of them, but it might be a case. So what about the actual PID controller design? What if I am leaving everything as it is, not fixing anything, and still want to design a PID controller? So let's see. What is the actual issue, or why did we fix one of the parameters or zeros? So let me copy this here and maybe up to this point, somewhere here. So this is a good point here. So of course I have to get rid of this and of this. So we have the system definition, we have the requirements. Now here, if we design a PID controller, Z1 and Z2 is not known. Therefore, we have Z1 and Z2. We calculate the closed loop. We don't even need to simplify it anymore. We get the numerator part and denominator part, take the coefficients, normalize them, and that's one side of the equation. The other one is s squared plus 2 zeta omega and s plus omega n squared. We add a residual polynomial. Now at this point, we don't add a residual polynomial here. We add 2 residual polynomials here, and I'm again going to display the worst case scenario here. You should never go ahead and do this, but I'm still going to do it here. So I'm choosing 2 poles for the residual polynomial because the PID controller is of order 1, the system is of order 3. Summed up, I will have a 4th order closed loop transfer function. I have a 2nd order desired polynomial, so I need 2 poles to add to the polynomial here in order to be able to equate both coefficients of polynomials. So therefore, I'll end up in s plus p1 and then s plus p2. And yeah, at this point, I'll get all the coefficients. By the way, I didn't plug in, again, real because they don't have to be real. Only the coefficients need to be real. They can be complex conjugate poles. Therefore, the coefficients would, again, be still real. Therefore, this is not a good idea, but still, hold on, we'll see. So we've defined our problem, hopefully. And there we go. Now, this is the reason why we should avoid this. Now, as you can see, we have P1 times P2 here, and then P1, P2 on their own. And we've also K times Z1, K on its own, and then K times Z1 times Z2, which is, by the way, the multiplication P1 times P2 times something else. Now, imagine you're in the classical exam, and you're trying to solve this. This would be a nightmare. So, yeah, there's a simpler or a cleaner way of doing this. So let's go ahead and do that. Let's fix the issues here. Now, instead of defining K, Z1, and Z2, let's define the PID parameters itself. And I can conclude that they are real because these will be the coefficients of the controller. So the controller would look like KDS squared plus KP times S plus KI divided by S. If you divide by S, you will get KDS plus KP plus KI divided by S. So that's one fix that we need to do. And the other one would be to choose A and B instead of P1 and P2, and again declare them as real coefficients, because they will be, again, the coefficients of the polynomial that I'm going to define here. A second-order generalized coefficient polynomial. And I'm choosing this equal to 1 because I've normalized it here, and this would be 1, so the highest order term would be equal to 1. So I don't really need to define this as as squared plus bs plus 1, because it would immediately be equal to 1 from this equation here. You can try it out. So if I do this instead of the previous one, so let me not delete this. Now you can see how much simpler the result is. The resulting equation set is. You don't have any multiplication at all here. Here we had 3 terms multiplied and 2 terms multiplied equal to each other. Here we don't have that. Now, an A is immediately popping out as 5, and then I can maybe define, if I am on a computer and have linear algebra, I might use the matrix notation here, or I could use some elimination, some Gauss elimination, or something else. Or I can even work my way out because I know what A is. So this would be depending on B, this would be depending on B, and this would be depending on B. And I can see that all these 3 equations have KD, KP, and KI on their own, and each controller parameter would be depending on B instead of A, because A is a number. So I can also see that even knowing A does not solve the problem, because this has infinitely amount of solutions for the fact that we have 4 unknowns for 3 equations, or 5 unknowns for 4 equations. So the reason why we started by pole zero cancelling or pole zero cancellation was the fact that this has infinitely amount of solutions. So therefore we didn't talk about the actual solution last week and this week, of course. But we're coming close now. So we can see that KD, KP, KI can be depending on one parameter here, and that will be the following. So we did see that B is a parameter. So if I want to solve this, I'm not going to be able to do that. So instead of solving the problem for all the undefined parameters or all the variables here, we can tell the solve function to only solve for A, KD, KP, and KI. So this way, what the solve function here is going to do, it will solve only a, kd, kp, and ki. It will look for the solution of these variables here. And if you provide for this problem 4 variables here, since there are 4 meaningful equations, then you will have a unique parametric solution. So the parameter b will be left out, therefore it will be the dependent variable here. So kd will be in terms of the not mentioned parameter or variable here, so b. So kd will be a solution that will have b in it. The same goes for kp and ki. So let's see, kp, let's call it fkp. So this will be sol.kp, and I'm going to solve kp, ki, and kd here. Of course, we can also solve for a. So fa, of course, is equal to 5. We've already seen that, but fkp is this. So it is 0.02 times b plus 0.1431, and that's it. And I can do this for kp, ki, and kd. Now, at this point, I have a parametric solution. Now, the question is the following. What should I do next? Because I have the parametric solution. What can I do next? Well, b is a variable, and it has a certain interval. For example, if I want to have stable closed-loop transfer functions, I need to choose a and b positive values. Therefore, positivity is important here, because if you prepare the root table for this polynomial, you will immediately see that a and b being positive is sufficient and necessary. Therefore, I could choose an interval for b that starts with 0.5, for 0.1, for example. Not exactly 0, because that would be marginally stable. And then increase b and see what the controller parameters are going to be. And then, of course, I can look for the best solution that fits. So, therefore, I'm going to define a b vector. Maybe linspace is a good idea here. Or I could also use a log space. It depends on your choice. You might do something like this, 0, 100, and then have maybe 200 different points here. And after this definition, what I'm going to do is I'm going to cycle through each element of this vector, and I'm going to then plug in the b value into this parametric solution here, kd, kp, ki, and then I know what the controller looks like. I can directly substitute the controller parameters into here, and I know the system. I can construct a closed loop. I can check what the step info gives me in terms of settling time and overshoot. And then I could try to determine and come up with the best one that fits in terms of settling time and overshoot requirements. So instead of using linspace, maybe we should use 0.1, and then step size is 1, and then maybe up to 10, or maybe. Let's start even simpler. Let's have this here. Let's have 3 values, 1, 2, and 3. So I'm going to choose each element of this vector, bvec, and then if I choose this ith element from bvec I, I'll get the b value that I'm going to substitute into. Now at this point, since a is already known, I don't really have to substitute into that, but I could look for kp val. So how can I do this? Well, this is a symbolic expression. It has b in it. I'm going to plug in a value into the variable b. So I can use subs here, fkp, instead of b, use b val. Now, since the only parameter is b, I could convert it into a double and see what the numeric value would be. So let's say kpval. So there we go. Having bvec equal to 1 up to 3, I can see that the kp values would be calculated like this. So I can repeat this for kp, ki, and kd, and even a. So let's have kd, ki. Let's also try fa. But since it doesn't have b in it, it might complain about that. Let's see if it runs. Okay, it didn't. It's good. So a val, and then maybe kd val. Let's run it again. There we go. We can see that a doesn't change because it's not depending on b, but kd val is like this. Now at this point, I have to plug in these solutions into the controller, so I need to construct the controller itself. Now, since I've used the parameters, I can define the controller like this. We have kd, kp, and ki, of course val. So this would be the controller that I've chosen if I take the value b equals 1, 2, and 3. So as usual, I'm going to look for the closed loop transfer function. I know what the controller is, comma gs. gs was defined here, so therefore we're good to go. And then info, step info would give me basically the info here. So info dot settling time and maybe info dot overshoot. Now, of course, this will give me something like this, and these b values here are not the only values that I want to check. If it's possible, I want to check a huge range with as many points as possible, and then try to pick one that's the best. So this is kind of an optimization problem, because the objective here is to get the settling time that is given and the overshoot that is given as close as possible to each other. So therefore, we need to have kind of a table that has all the possible controllers in it and their results in it, so that I can at least see what's really going on there. So therefore, let me construct a table that will be storing the values that I want to store. So what should we store? Well, basically, we need kd, kp, and ki, and we might also track a and b, because these are responsible for the residue polynomial. So yeah, maybe also the settling time and overshoot. So at least these should be stored in a table. So in the table, each row would have a solution, kd, kp, ki, and the results associated with that solution. So the amount of rows that I need will be depending on the amount of elements of this vector here. So therefore, I need length bvec as the row size. And the column size is basically 1, 2, 3, 4, 5, 6, 7 here in this case, because each column will be corresponding to kd, kp, ki, a, b, and tsos. So, of course, you don't really have to pre-allocate the table here, but it's a good strategy, because if we increase the points in here, then each cycle MATLAB would then basically copy, and that's not really ideal. It will slow down if you especially have a computer that's not up to date. So Of course, you can define an empty array here and then do something like this. We have, for example, table equals, and then again the whole table, and then the next row is this. Yeah, that's possible, but it's not ideal, so I'm going to pre-allocate the whole table and access each row for each b val here, and then fill it with the data that I need to fill. So the table, the ith row, and the first element should be equal to kd val, because that was the protocol that I've defined in line 35. And therefore, I'm going to store kd, kp, and ki. You might ask yourself why I've chosen the kd, kp, ki, or whereas the controller is called the PID, so maybe kp, ki, kd would be a sensible choice. But here, if I access the first three elements, that's also the numerator of my controller. Therefore, I arranged it like this. This is not imperative. You can change it as you wish, as it fits you. Now, so the first element is kd, second element is kp, third element is ki, and then we have a, which is not really that necessary, but I'm going to change that in a minute. And let's have also b val, so this would be 5, and this is b val, and then the sixth one would be then the settling time. So therefore, there we go. Now this one would be then overshoot. Now once we are done, let's also use fprintf, and then let's cycle through this table again. Oh, I equals this. And I'm going to use this, for example, here, and a tab maybe. Or we might also make it manually. So let's go ahead and do that. So this would be kd, and then kp, ki, and then this would be a, this would be b, we would have ts, and os. You don't really have to use fprintf, but yeah. So let's say row 1, 2, maybe we should use the next line, 3, 4, 5, 6, and 7. So of course I need to also acquire the row here, the ith row, and all the columns would be the row element here. So there we go. Now as you can see, now I have a table that looks like this, and for some reason the tab didn't work here. Let's place in these here. Run it again. Now, here we can see that kd is increasing a little bit, kp is increasing a little bit, ki is also increasing, a is fixed, that's nothing new. We have all the b values here, and then the settling time seems to be decreasing here, and overshoot is increasing here. So yeah. Now, of course, we will not use such a narrow range. We'll hopefully increase the step size here. And let's start with 0.1, and then also 3 is also not sufficient. As you can see, the table can grow. And yeah, we have different settling times and different overshoot values. So what should we do? Basically, we can also see that somewhere here, the settling time was small, and then it increased, and it started to decrease again, whereas the overshoot does not change that much. Now, at this point, it is important to check what the system gain is, because if you look close, we have 100 here. Now, if we are multiplying with 0.03 here, this would correspond to 3. So, yeah, we have to take this into account. So, if we are, for example, looking for 0.1 steps here, we might need to have a finer grid here, or even a smaller starting point. Let's also decrease that, because at some point we will have a performance issue, because too many points, too large of a table, it will slow down. Now, I was looking for settling time 4 and 10% overshoot. Now, according to this table, I'm not really getting both at the same time. But if I'm okay with a little bit of deviation in the settling time, I might go ahead and choose this one here, because this seems to be the solution that I've acquired by using pole zero cancellation. So that might be still on the table. Now, it seems like up to this point, I can safely assume that the settling time, if it's even going to be dropping down again back here, I'll see that the overshoot is still increasing. Now, I might use, for example, 10 here. Hope that my computer is not going to slow down that much. Let's see. It takes quite some time. Yeah, finally. Now we can see that the settling time is still dropping, and the overshoot is also very high here at this point. Now, yeah, somewhere here in the table, hopefully, we should have a good solution. There we go. Now, since the gain here is very high of the system, you can see that I'm not even ending up in huge control coefficients here, because if you multiply this with 100, you have 11, 31, and 24. So sometimes KDK PKI can be small because the multiplication will be great enough. Now the question is the following. I have a table that has potential solutions in it, and how can I determine if one of the solutions is a good one? How can I choose a solution from this? Because eyeballing is not a good idea. I might miss it, and there might be a case which is closer to the requirements, but I might not be able to see it, and I might want to increase this interval even further. For example, a good idea would be to, in terms of computational power, it would be a good idea to choose 10 to the power of -2 and 3, for example, with, for example, 500 points. Now, this is logarithmic scaling because this would hopefully include the small values and huge values equally at the same time. So if I run this, still a lot of work, but now we have even huge values included in our table, and even the small values that we've seen as well. So it's a good strategy to use log space, because if you're deciding on a certain interval, you can narrow down your interval into that. So how can I determine if a solution is a good one? Now, one approach would be the following. I know the settling time and the overshoot. And I have also the settling time and overshoot value here. So I might look for the difference, for example, between the settling time and the settling time that's read from the step info, also for the overshoot and the result from step info. So yeah, therefore we might go ahead and add two more columns. Let's say E1 and E2. So this is for settling time, this is for overshoot, or ETS and EOS. Let's have an underscore. So let's go ahead and define them. Now, at this point, we have settling time. So what we can do is we can look for the absolute difference between the settling time and info.settling time. And the same goes for overshoot. Now, I guess this is not divided by 100. So therefore, we have to divide this into 100. So if we have overshoot here, we are going to look for overshoot minus info.overshoot divided by 100. So let's include them in our table. So 8 and 9 would be then these values here. Therefore, I need to ETS is this, and then EOS is this, row 8 and 9. Using this fprintf is also neat. You can also go ahead and use fopen and then give it a name. Let's say debug.txt, and fclose, fid. And if you provide this fid to this, then it will no more output this into the standard output, but it will write it to a file, and maybe navigating a file can be sometimes easier. So of course I have to increase this to 9, and then we can run this. Hopefully there will be a file output here. And it did not. We need to write onto a file. Okay, we have debug.txt. Now we can navigate in a file. It's not really important, but sometimes this could be a good idea. If you're, for example, preparing a report, then dumping it into a file might be a better choice. Then you can copy and paste it even better. So now we have an error value here, which is didn't be updated. Oh, which is not correct at the moment. So let's fix this. Let's have overshoot here. So now, there we go. Now that's updated. Now we know that we had a 4-second settling time requirement. We have 3.53 here, and the difference between them is 0.47. Now we had 10% overshoot. We have 10.16% overshoot. And the difference, it does not show as many digits as it should be. So maybe we should also increase the amount of digits here. because this one was the problem here. So maybe for the overshoot, we should have maybe 5 digits. So let's again fix that and see. Now, even though I know the difference between, there we go, we can see now. Even though I can see the difference between the requirement and the resulting value for settling time and for overshoot, I'm still not close to determining which one is the optimal solution that I'm looking for, because there are too many values and there are two basic requirements here. If I would have had just the settling time requirement, what I could have done was to look for the minimum value in this column here. I have 45, it goes down to 44, and somewhere down here, I can see that, for example, this solution seems to be the optimal solution in terms of settling time, and that's obvious because we have 3.93. But this is not the best solution in terms of overshoot. If I'm looking for overshoot, I'm going to probably choose one of these here. Let's see. It still drops down. It seems like this one is the best solution in terms of overshoot. So how should I choose based on settling time and overshoot? Now I can achieve this by combining the errors. Now, of course, I cannot add them directly together to each other because one of them has seconds, and one of them is percentage. So yeah, we need to somehow convert them into the same data. So it's not possible to combine them as they are, but this is a difference between the actual value, the set point, and the resulting value. And this is also the same. But if I'm looking for error, for example, if the value is 3.53, if the value is 4, then 0.47 has a meaning. But if the value is something else, for example, if it's a higher value like 12, then this difference here has is not equally bad or good. If this is good or bad, I cannot really determine based on the difference here, but instead of using the absolute error here, I might look for relative error. If I have a huge number and a low error value, that should be relatively good. But the inverse is also true. If the value is 1 second and the difference is 1 second, then I have 100% error, relatively bad. So let's go ahead and instead of looking for these error values or even these differences here, let's change them and convert them into relative errors. So how can I do this? Well, I have the difference here, and my set point, the actual value, is TS, so let's divide by TS. I have an overshoot value, I'm taking the difference here, so let's divide into OS. Now these are relative errors, so hopefully, if we didn't mess up anything, let's see. Now we can see that in terms of difference, we can see that 0.12, 0.11, this is the percentage. If I multiply this with 100, let's do that too, then I'll get percentage here. Both are percentages. So I can, at this point, add them, combine them, because they have the same unit. So there we go. Now this means that this is approximately 12% of the value in terms of settling time. So 0.47 divided by 4 times 100 gives me this value here. And in terms of overshoot, I have 1.56% error. So now this is percentage relative error. And for example, here somewhere we have 6% settling time error and 14% overshoot error, etc. Now they also increase. You can see that it is 176. Because I was looking for 4, it is twice as much almost as the set point value. And this is almost 100% off the value. So therefore, this is a good metric in this case in order to determine the point that is optimal. Now, it is obvious that I'm looking in at this interval here, because after this point, it gets only worse. So my optimal solution should be somewhere in this interval. So now, how can I combine them? Well, what I can do is I can do the following. Let's say these mean equally to me, which means that I want to be as good as possible in both of them equally. So 50% of this and 50% of this combined should give me the metric that I'm looking for. So let's increase this up to 10. Let's add another column. And this column now should be the objective. And the objective is chosen as equally. So 50% of the relative error in settling time plus 50% of relative error in overshoot. And I'm going to set this objective value. Once I've done this, before I go on, I should maybe add another row. So let's say OBJ, and we should be good to go. Now we have the objective, and you can see that the index here is increasing, which means that the first one was the best solution in this case. Still increasing, still increasing. And there we go. Now we can see that it seems to be the solution here. That is the best fit if I'm interested in equally meaning, if I'm assigning equally meaning to settling time and overshoot. So yeah, now since we have the solution, or since we have just one metric and we want to minimize that, we can call the min function here on the last column of the table. So I'm looking for the minimum value of all the rows but the last column. I can also write in 10, but if I'm adding and if I'm still keeping the objective in the last column, then this is a better way of doing it. So now I didn't use only minimum here. I'm also acquiring the point where this happens, so the index, so I can retrieve the whole solution back. Now the row that I'm interested in will be table and then index row and all the columns. Now let's also define a controller, and this was what I was talking about. This is 1, 0, and I will use row 1 to 3. 1 up to 3 here. Because these are the coefficients and they are ordered KD, KP, KI, so I can use them directly here. Now at this point, I've defined the transfer function here. Let me also use this here. So let's rearrange this like that. I can, by the way, I can combine them, but it's not really that important at this point. So this method is called tabulation because we are using a table. We are writing all the values into this table, and then we're looking for the best solution in this table. The crucial part here is to construct these metrics here that determine how good the settling time is, how good the overshoot is, and I also need to convert them into the same unit because of the fact that I want to combine them, maybe equally, maybe not equally. I'm going to touch upon this in a moment. And then I have a objective here which tries to determine how good the solution is. So I need to associate a number to the solution and how good the solution is. So therefore, minimizing that objective function or value in this case should give me the optimal solution or the best solution that fits in terms of settling time and overshoot. This is kind of a numeric approach, by the way. You can see that. So therefore, it's still applicable, but it is numeric. So we should be aware of that. So let me take this whole thing here in order to be able to compare how good we did or what's really going on in this case. So now we have the closed loop here, therefore we have step info, step all the results here. Now here, of course, this is not the case. I am using basically this here, so let me copy this. Of course, this time around, I might go ahead and calculate the zeros, or I can also do something like the following. I can say that row 1, oh, is it still row? Okay, of course. Now this is KD val. If I want to still normalize in terms of the coefficient that I'm going to read from the root locus, I can do the following. I know that this is KDS squared and then plus KPS plus KI. Now, if I divide into KD, I'll get basically what I want. I have to divide into KD if I'm looking for, if I'm trying to exclude the gain of the controller. Since I was trying to use S plus Z1 and S plus Z2, and I wanted to isolate K here, you can see that 87 and 88 are the same. So instead of providing the whole vector here, I can just use 1 comma kp val divided by kd val, and then ki val divided by kd val. So this way I'll end up in only adding the zeros here, and if I click the root locus plot, at that point I should read the value of kd val. So I have the root locus, all the poles and zeros, and hopefully we should be good to go. There we go. Now this is the solution that we've acquired. And yeah, in terms of settling time, we have 3.5256. Overshoot is 10.1567. Now, if you look close, we can see that we again have a pole zero cancellation at this point, and another one is almost a pole zero cancellation. This is not exactly a pole zero cancellation. Maybe this has also some numerical differences. Yep, this is also not exactly a pole zero cancellation, but it is so close that I can assume that there are two pole zero cancellations. Now, this question that we have here, or this system and the requirements here, are special requirements. And for this system only, and these specifications only, we can see that the strategy for this PID controller is to design a PD controller, because we found the same solution as in A. So basically A and B are resulting the same. And we can conclude that for this system, a PD controller for the given settling time and overshoot are ideal. And we've also proven that numerically. Now, for any other system or any other settling time or overshoot requirement, they may not coincide. So in A, you might find a solution, and in B, you don't really have to find the solution as found in A. It turns out that the subsolutions, because pole zero cancellations are a group of solutions that are included in B, in tabulation, are the ones that we are looking for. But this is a special case. This doesn't have to be the case. So we have now the tool that gives us a huge table that tries out all the possible solutions here and tries to find the best solutions by associating the relative errors and combining them equally. So of course, for this system, it may not be that important, but it is possible to change the weights here, because these are weights, and the restriction here is to have two weights, W1 and W2 in this case. Now they should add up to 1, and each of them, omega 1 and omega 2, should be between 0 and 1, so in this interval. So if you have 3, for example, you can extend this concept here. If you're trying to combine 3 different columns, in this case, you can do the same here. So by choosing 0.1, one of them 0.1, one of them 0.2, for example, you can end up in choosing 0.7 for the other one. Or 0.5, maybe 0.25, 25. So it depends on your choice, but you should choose weights between 0 and 1, and all the weights should sum up to 1. So this is called Pareto optimization, because we're kind of projecting the 2 dimensions into a dimension, and we're optimizing on that dimension. Therefore, this is a Pareto optimization problem in this case. A multi-output or multi-objective optimization is already hard on its own, and in this case, we've only showcased a solution method that is trying to do its best in terms of settling time overshoot and combining them equally or in different weights. Now, if we didn't have settling time, which was the last week's design problem, then we could have tried to change or try some settling time values here. But keep in mind that we have already the settling time and the overshoot here. So they are already given. So we are trying to therefore optimize this solution so that we have the best settling time and overshoot, or the closest to the requirements here. So now, this tabulation code can depend on your needs. You can change it, alter it as you want. This is a generic idea, so you can use the idea here. We used the system, we used the requirements, we built our problem, but it was not enough because we had more than one solutions. Therefore, we used logarithmic space here in order to cover all the range as fast as possible. And then we ended up in choosing the B values here. Of course, let me note that we don't really have to choose B here. We might also choose Ki as a free parameter. So then you need to omit the Ki parameter and provide B here. So then it will solve A and B in terms of Ki in this case, and Kd and Kp will also depend on Ki. So that's also possible, and then you have to grid basically Ki. You have to vary Ki in an interval. And then look for the best solution, and it should give you basically, hopefully, the best solution. So, there we go. Let's run it one more time to ensure if it's running. Now, of course, this is a PID controller design method. Now, but this is not the only method. We have looked for pole zero cancellation. That might work, but it is really restricted. because we're fixing one of the variables, and that's it. We can also use tabulation, but we can also use the Ziegler-Nichols method. So in order to design a controller with the Ziegler-Nichols method, we need the following. So let me take this here. There we go. Now, the Ziegler-Nichols method here calls for the following. Before you design any controller, you need to examine the open loop system. So, and we're interested in the marginal stability of the open loop system because that will hint us for Kp, Ki, and Kd values. Now, let's first find the marginally stable closed loop and the p-type controller in this case that results in marginal stability. Now, there are numerous ways of acquiring this p-type controller coefficient, but I'm going to choose one of them, which is going to be the most suited for MATLAB. So let's define K, the p-type controller. Let's define the closed loop, K times GSS, and then 1 plus K times GSS. So now let's get the numerator and denominator part, TSS, and let's look at the denominator. So this is the denominator that we're interested in. Of course, you can use R locus, by the way. It's perfectly fine. But if you're on a pen and paper, then this might be the solution that you want to go for. So this here should have a pole at plus minus j omega, because this is the j omega axis and this crossing is marginally stable. So I know that s squared plus omega squared equals 0, or in other words, s squared is equal to minus omega squared. Or in other words, s is plus minus j omega. So this is a fact. I know that this is. So since I have the characteristic polynomial here, what I can do is I can go ahead and plug in j omega into this polynomial, and it should satisfy this pole, because it's the root of the characteristic polynomial in the closed loop at the marginally stable j omega. So therefore, I can substitute, and before I do that, I need to define omega. I can substitute j omega into s, 1i times omega into s. So this would give me something like this. There we go. Now, of course, p omega should be equal to 0, but since this is a complex valued function or polynomial, the real part should be equal to 0 and the imaginary part should be equal to 0. So if I say p omega is equal to 0, what I really mean is this is equal to 0 plus 0i. So therefore, I can construct again a problem or a set of equations that takes the real part of p omega, equates it to 0, takes the imaginary part of p omega, equates it to 0, and I can solve this. You might be asking, how can I do this using a pen and paper? Of course, it's a little bit of a struggle if it's a high order polynomial, but it is regarding the fact that it is already a high order polynomial. But at this point, you can almost see what the solutions might be looking like, because we have 10 times omega I and then minus omega cubed I. So these should be summed and equated to 0. Therefore, I can see that omega 0 is one of the solutions, and omega squared equals 10 is also one of the solutions. Knowing omega squared gives me k values. So therefore, it may be simpler than it seems. So let's take sol.omega here, and k-val maybe also k. So let's see what the omega values look like. I know that one of the values should be 0, the other one should be square root of 10. So square root of 10 is this. So I might eliminate again the negative values here, but I don't really have to, but let me do it here. I'm including the 0 one because I'm interested in that. Normally I'm not, but in this case I am. There we go. So k-val, omega val. There we go. Now, at this point, I need basically the p-type controller, 0.7, so k critical is 0.7. And I have also 3.16, therefore this would be omega equals to 3.16 here. So I need to note down this one here. And by the way, this can be converted into 2 pi, 2 times pi divided by the period here. Therefore, I might go ahead and change this into t critical is equal to this. So let me see. It's 19883. So that's basically the crucial part here. So then we will use this and a table that gives me directly KD, KP, and KI. So these will be directly given based on these two definitions or values here. So this is important because the Ziegler-Nichols method here gives you directly a controller that stabilizes the system in the closed loop and has a certain characteristic to it. We don't give a settling time, we don't give an overshoot requirement to this design method because it's not using it. So it only needs the open loop, therefore it looks for the marginal stability point and the frequency and maybe the period of that. And the critical k value that achieves that marginally stable point, and that's basically it. Then you will use a table, which I'm going to show in a moment, and you will end up in a PID controller. So the crucial part was to get the marginally stable point, and this part will be easy. So before I go into the details of Ziegler-Nichols, let me also talk about phase lead controller here. Now, for the phase lead controller, all the stuff in A and B applies. So the method does not change. All the stuff does apply for phase lead controller using pole zero cancellation and tabulation. As a matter of fact, it applies to all the controller designs that can be done via the algebraic method, because we do almost always the same over and over again. We take the structure of the controller, we know what the unknowns are, and if we are using the algebraic method, we take the coefficients as definitions, KD, KP, KI, or in the residual polynomial, we take s squared plus as plus b, or it could be even generalized for nth order residual polynomials. And then we calculate the characteristic polynomial of the closed loop, take the coefficients and note it down. That's one side of the equation, the set of equations. And the other side is determined based on the requirements, which are, for example, settling time and overshoot. And we construct a PDS using a polynomial s squared plus 2 times theta times omega n s plus omega n squared. And if it is a higher order closed loop than 2, then we add residual polynomials to them. We multiply them, take the coefficients, and build the problem using the algebraic method. And then we solve it, and that's it. If you're using tabulation, then you will always use tabulation for solutions that are infinitely amount of solutions. So for problems which have more parameters than equations, then you can use tabulation. If there's a unique solution, then you automatically don't add up in tabulation. So that's it. And for pole zero cancellation, you just choose one of the poles and place a 0 on top of that, and you've already defined some part of your controller, then you're looking for the remaining part. So therefore, I'm going to skip for the sake of the length of this video. Therefore, we'll see how to design the phase lead and phase lead controller with pole zero cancellation and tabulation. Now, here in my notes, I have the zeta value calculated here. I have omega n. We've constructed the PDS here. We have this controller here. And if you work your way out, you can see that this will be the closed loop. We've seen this already. And we add S plus P. We construct a problem. We solve it. Now again, here we have this solution here. But as a matter of fact, you should never ever define K, Z, and use this here, because the problem is complicated for no reason. Now, this is the solution that we've end up in, and we've chosen the solution. You can see the root locus plot, you can see the step response. Now, for the more general case, again, I have S plus Z1, S plus Z2, but here in this video, I used KP, KI, and KD, and you should do that too. So, if you've done that, there's this part here, Z1, Z2 times K, and then this is P1, P2. This is really not that necessary, so we should avoid that. Now, here, it's also possible to look for the raise the polynomial, because if you remember, in our case, we had KD, KP, and KI. Now, it is possible to get KD, KP, KI in terms of B, which we do here. So if I plug that in back into my residual polynomial, which is, let me find it here, which is S squared plus AS plus B. So B is already B, and A is equal to 5. So I can work my way out and see what B should be for closed loop stability. Now, if you choose something else, like we've chosen K as a free parameter, then you can also determine all the K values or the interval for K that will end up in stable closed loop transfer functions. So in this case, for example, by checking this residual polynomial, since our free parameter will be K, we can see that 100K minus 286, 2 should be positive, since this is a second order one. If not, you can use the root tabulation method or any other method for stability analysis, but I don't really have to check PDS because that's already by definition stable, but PES can determine the stability here, and I can see that there's a lower value. For example, 0.002, I guess, would be then the lower bound for K, like this here. So if I'm using lint space or log space, I should take into account that this is the lower bound for K. Now, in order to have some diversity, I've chosen a different path here in the video, but you can also examine the whole solution in the PDF, or you can also try to change the strategy here. You can look for different variables as free variables. You can experiment on your own. You can choose, for example, KD as a free parameter, and I'd highly advise you to do that, because you will see then how different the solution can look like, even though you're looking for the same solution. Now, here is a more abstract definition of the thing that I've talked about, namely that we have one error and another error, or two possible objective functions, and we're combining them using alpha and 1 minus alpha if alpha is between 0 and 1. Now we can use also alpha and beta and say alpha beta sum should be equal to 1, and alpha and beta should be in the interval of 0, 1, or you can also use alpha and 1 minus alpha, because if you have 0.2 here, then you're extracting that from 1, which ends up being 0.8 here. So therefore, we combine 20% of this, 80% of this, and end up in an objective function, or just 1D signal here in this case. Now, the optimal solution for this here in our notes is this, and I've given you the table. Now, this is the reason why we should never ever go ahead and use Z1, Z2, P1, and P2 because first of all, we've neglected the part where k should be greater than and almost equal to 0.03 here, because it was 0.0028, I guess, something like that. So it should be starting from this here, this lower value. But also, we can see that there are complex values, complex conjugates, pairs here and there. If you use MATLAB solve, you will get 4 different solutions, because MATLAB will not know if Z1 or Z2 is the same if they are complex conjugate pairs. So it will give you 4 times the solutions that you might expect, because 2 for this and 2 for this P1, P2 pair. So you have to eliminate your way through, and yeah, it's not really nice to have this. So instead of this, please go ahead and use the method that I've shown you in this video, because it makes more sense and it's far more simpler than that. Now, in the Ziegler-Nichols method, I've already started this and I've calculated the values up to this point, but here is a more mathematical representation of the solution. You can see KGS divided by 1 plus KGS is the closed loop here. We work our way out and we plug in j omega into the polynomial, and we equate the imaginary part to 0, the real part to 0, and we end up in these values here. And you can see these are the values. Once you have these values, you can use the Ziegler-Nichols table that you might have in your notes. If not, you can just Google it and it will pop up. It is like the following. If you want to design a PID controller, because there are different versions for Ziegler-Nichols and also different algorithms as far as I remember. If you have a critical K here, take this multiplication and choose this as Kp. Now here you can see it is within the stability bound. That's 1. And then you're adding a integrator coefficient, or an integrator with this coefficient, Kp divided by 0.5t, which is t, where t is basically the omega value and the period of that. So it's possible to directly calculate this. Also, you are choosing kd like this. So these are formulas, and you're plugging in these 2 values, and you end up in the PID controller that you're looking for, hopefully. Now, this is the controller, and then this is the closed loop, and this is the step response. Now, let me remind you that we didn't use settling time. We didn't use overshoot. Therefore, we cannot expect the response to have a certain settling time or a certain overshoot value. Now, the only thing that the solution has, as far as I remember, is that the damping value is 0.707, as far as I remember. So you might try and check out what the zeta value of this is, because it most of the time tries to have 0.707 zeta, or damping ratio. But other than that, we cannot define the system characteristics in terms of closed loop transients here, but we have a stable and working solution. Now here we can also see what the where the zeros are, and yeah, that's basically it. Using Ziegler-Nichols method, you can only do this much. Here's also the code. Now for the phase lead controller, we define our structure, and our algorithm is always the same, but we can choose one of the zeros on top of the pole of the open loop system. Z could be 2 or 5. We've already talked about this. For example, if you choose 2, we end up in this closed loop here. Now the problem becomes this. If we solve this, we get this controller here, and we have then the closed loop response here. Now phase lead controller makes sense because ideally we were looking for a PD controller, so a phase lead should also work because they have the same effect in this case. Now, if we want to use tabulation, then we are not fixing anything, and you can see that P1, P2, P, K, and Z are the unknowns, and we have only 4 equations. Therefore, there are infinite amount of solutions. Again, we are not using the same objective function combination method here, and we again use a table. Now, in this table, we have again overshoot, we have settling time, the difference, and then combine them as relative errors here. and optimize it, and we end up again in such a solution. Of course, these methods here are, again, as I've mentioned, numerical solutions, but let me give you a hint. It is possible to parameterize the controller parameters. So if you choose one free variable, in our case I've chosen b, but maybe, let me go up here, maybe instead of solving for a, kd, kp, and ki, we might use kp or ki as free parameter, change this into b. At this point, it is possible to define or define the parameters kd, kp in terms of ki. And I can plug this into FSS here, and then the closed loop would be a closed loop with one parameter being ki. Now, the residual polynomial can be defined in terms of ki. The numerator of the controller can also be defined in one variable. Now, if you have a polynomial and just one variable, then you might use root locus. So that is important to note. So maybe you might want to think about this, because if you have just one parameter here, you can examine this using a root locus. If you have only one parameter here, you can do the same, and that might give you some hint. So that's it for this week. I will upload this PDF, and you will hopefully be able to access this PDF. And that's it, basically. See you in the next video.